Atoms in Motion is the famous lecture introduction. This two-year course in physics is presented from the point of view that you, the reader, are going to be a physicist. This is not necessarily the case, of course, but that is what every professor in every subject assumes. If you are going to be a physicist, you will have a lot to study. 200 years of the most rapidly developing fields of knowledge. That there is so much knowledge in fast that you might think that you cannot learn all of it in 4 years. Actually, you cannot. You will have to go to graduate school too. Surprisingly enough, in spite of the tremendous amounts of work that has been done for all this time, it is possible to condense the enormous mass of the Sun to a larger extent. Thus, the two-point law will summarize all our knowledge. Even so, the law is so hard to grasp that it is unfair to you to start employing this tremendous subject without some kind of map or analysis of the relationship of one part of the subject of science to another. Following these preliminary remarks, the first three chapters will therefore outline the relation of physics to the rest of the science, the relations of the science to each other, and the meaning of science to help us develop a feel for the subject. You might ask why we cannot teach physics by just giving the basic laws on page one and then showing how they work in all possible circumstances, as we do in Euclidean geometry, where we state the axioms and then make all sorts of deductions. So, not satisfied to learn physics in 4 years, you want to learn it in 4 minutes. We cannot do it in this way for two reasons. First, we do not yet know all the basic laws. There is an expanding frontier of ignorance. Second, the correct statement of the laws of physics involves some very unfamiliar ideas which rely against mathematics for their description. Therefore, one needs to consider amounts of preparatory training even to learn what the words mean. No, it is not possible to do it that way. We can only do it piece by piece. Each piece or part of the whole of nature is already merely an approximation to complete truth. All the complete truth so far as we know is first, everything we know is only some kind of approximation, because we know that we do not know all the law as yet. Therefore, things must be learned only to be unlearned again, or more likely to be corrected. Principle of science. The definition almost is the following: the test of all knowledge is experiment. Experiment is one choice of scientific feature. But what is the source of knowledge? Where do the laws that are to be tested come from? Experiment itself helps to produce this law in the sense that it gives us hints, but also needed is imagination to create from the hints the great generalization to get at a wonderful symbol, but they chain pattern beneath them all, and then the experiment to check again whether we have met the right guess. This imaging process is so difficult that there is a division of labor in physics. There there are theoretical physicists who imagine dust and gas at new laws, but do not experiment. And then there are experimental physicists who experiment, image dust and gas. We said that the laws of nature are approximate. Thus, we first try the wrong ones and then we find the right ones. Now, how can an experiment be wrong? First, in a trivial way, if something is wrong with the apparatus that you did not notice, but within are easily fixed and checked back and forth. So without snatching and such minor thing, you can how can the results of an experiment be wrong? Only be being inaccurate. For example, the mass of an object never seems to change. A spinning top has the same weight as a steel one, so a law was invented. Mass is content independent of speed. Thus law is now found to be incorrect. Mass is found to increase with velocity, but appreciable increases derived velocity near that of light. A true law is if an object moves with a speed of less than 100 miles a second, the mass is contained to within one part in a million. In some such approximate form, this is a correct law, so it's in practice one might think that the new laws make no significant difference. Well, yes and no. For ordinary speech, we can certainly forget its adjunct symbol container mass law as a good approximation. But for high speed, we are wrong, and the higher the speed, the more wrong we are. Finally, the most interesting philosophically, we are completely wrong with the approximate law. All the temperature of the world has to be under even though the mass change only by a little bit. This is a very peculiar thing about the philosophy or the ideas behind the laws. Even the very small effects sometimes derive from powers changes in our idea. Now, what should we teach first? Should we teach the correct but unfamiliar law with its change and difficult conceptual ideas? For example, the theory of relativity with its four-dimensional spacetime and so on. Or should we practice the simple contact mass law with evenly approximate but not involve such difficult idea? The first is more exciting, more wonderful, and more fun, but the second is easier to get at first. It is the first step to the real understanding of the first idea. This voice arrives again and again in teaching physics. At different times, we shall have to resolve it in different way, but at this stage, it's a worth learning. But in now, how accurate is it? How it fits into everything else and how it might be changed when we learn more. Let us now proceed with our outline, our general map, or our understanding of science today, in particular physics, but also other science on the periphery. So that's when we later concentrate on some particular points. We will have some idea of the background why that particular point is interesting in how it fits into the big picture. So, what is our overall picture of the world?